control more closely relates to dynamic path control using reachability and performance metrics. We will obtain those performance metrics using tools such as the Cisco IP SLAs. So let's switch gears and transport ourselves to a scenario of Internet branch office connectivity with dual connections to different ISPs. The edge router is configured for network address translation, or NAT, and routing into both ISP networks. This is not uncommon and will most likely be ruled by default routes for outbound traffic to keep things simple, especially in the case of branch offices where you are not likely to run BGP or any other routing protocols toward the ISP. In this example, we are using equal cost static default routes, which allow us to take advantage of load balancing rules in Cisco IOS. This allows us to use both links on a per destination basis. NAT will apply to traffic according to the selected upstream interface that results from the load balancing algorithm. In this scenario, the router accomplishes failure detection if we experience direct link failures. However, if the infrastructure of one of the ISPs fails, the use of static routes prevents us from rerouting all traffic into the connection to the other ISP. So, if there are non-directly connected failures, static routes will behave statically, and they will not be able to reroute to our backup link. What can we do about this? Well, the first approach could be to run a dynamic routing protocol, and this would help the router to identify remote failure conditions. This may be unlikely in the case of a smaller branch office. It also requires interaction and integration with the ISP, but it may be the best choice if this is a critical branch or if your traffic volumes require it. An alternative that will not require routing protocol changes is suggested here. Why not use either static routes or policy-based routing, PBR, but make them subject to reachability tests toward critical destinations, such as DNS servers? In other words, if the DNS servers of one of the ISPs go down or are unreachable, remove the static route toward that ISP. At this point, we assume that with failed DNS connectivity, it is also considered a failure of the ISP's network. You can perform reachability tests with Cisco IP SLAs that probe the DNS servers frequently and are attached to our static default route. Let's see how this is done. As usual, we will define a strategy for this solution and the tools we will use. We want to track the reachability of certain objects, this time the DNS servers, so we will use the object tracking feature. These are capabilities available in the Cisco IOS for static routes. Those object tracking features can use IP SLAs to send different types of probes toward the desired objects. In order to associate the results of the tracking to our routing process, we can use two options. One is policy-based routing, which allows you to set the next hop as part of your route map configuration. This allows you to tie the next hop to the results of the object tracking. In other words, the next hop will become available and operational only when the object is reachable. The second option is static routes. With this option, you can tie the tracked object directly to the static route, which will appear in the routing table only when the tracked object is reachable. Because we will use IP SLAs, here is a quick review. You also studied these in your CCNP Route ILT course. IP SLAs use active traffic monitoring for measuring network performance. They send data across a network to measure performance between multiple network locations or across multiple network paths, such as those in the figure. IP SLAs simulate network data in the form of IP SLA probes. They also simulate IP network services and collect network performance information in real time. The information collected includes data about response time, one-way latency, jitter, packet loss, server response times, and so on. In its simplest form, IP SLAs will at least verify whether a network object, such as an IP address on a router's interface or an open TCP port on a host, is available and reachable. Because IP SLAs are accessible using CCNP, or Simple Network Management Protocol, it can also be used by performance monitoring applications, such as Cisco Works Inter-Network Performance Monitor. As an additional feature, CCNP notifications based on the data gathered by IP SLA operations allow the routers to receive alerts when performance drops below a specified level and when problems are corrected. These thresholds can trigger additional events and actions. Now we will use these tools in the scenario shown here in the top left panel. This time R3 represents the branch office. Using IP SLAs, we are going to track the liveliness of the DNS servers with the IP addresses of 10.0.8.1 and 10.0.8.2. We will then tie the results to static default routes on R3 to redirect traffic. The IP addresses aren't very realistic for Internet DNS servers, but this is just a test example. Now, upon DNS failure, the IP SLA probes will fail and the static default routes will be removed, rerouting all traffic toward the other ISP. Our strategy results in a series of configuration steps listed here. Note the dependencies between all of the features we are using. After verifying the base configuration and reachability in our second step, IP SLAs need to be defined in terms of the IP addresses to probe. In our example, the DNS servers. We also configure the frequency of the probes and other parameters. It is very important in our third step that the IP SLA configuration is working and that we are able to isolate problems during the configuration. If the IP SLA fails, the dynamic routing function we are trying to configure will not work. Our fourth step uses tracking options. The tracking command allows you to link the IP SLA probes to a tracking option that will then be associated with a static route. In step 5, it is time to attach the tracking objects to our static default routes. This way, if the probe fails, the static default route will be removed from the routing table, and the next best default will be used toward the other ISP. We will simulate this by bringing down one of the DNS servers represented by loopbacks in our lab routers, and then verifying the dynamic operations of routing changes. So in our first step, we need to verify reachability from router R3 to the DNS servers. That's going to be, in our case, a simple ping toward the DNS servers. In this example, we can reach the 10.0.8.1 server. And the 10.0.8.2? We can also reach it. That was simple enough. Our next step is to configure the IP SLAs. We do that with the IP SLA command syntax shown here. With this command, we define the probes themselves, and we need to configure it on R3. So, let's do that. Our first probe is number 99. 99 is simply a reference number to be used when attaching or assigning the SLA to our object tracking configuration. The number is only locally significant and has no special meaning. It will not be on the other routers involved in this probe. This SLA will use ICMP echoes to send the probe. We point it to our first DNS server at 10.0.8.1. For that, we use the type echo command. Remember, this is one type of probe that we can send. In this same configuration mode, we can specify other probes, such as TCP connect, EDP echo, probes measuring jitter, and others using similar commands. You can see the options using the context-sensitive help. Notice that we enter a different configuration mode. You can further tune your IP SLA by defining frequencies, thresholds, and timeouts for the probes. Our second probe is number 100, and it points to our second DNS server. Notice in the syntax that you can change the source IP address of the probe and source it from a specific interface for added flexibility. For instance, you could source your IP SLA probe on loopback interfaces and then identify them more accurately in your network and be able to build access lists, configure firewalls, and other filters to allow this type of traffic. Other parameters that we can configure as part of our IP SLA probes are related to how often you want to send the probes with the frequency command. The default is every 60 seconds, but in this example, we will configure a frequency of every 10 seconds. You can also configure the timeout, or how long the IP-SLA configuration waits for a response to its request packet. The default is every 5,000 milliseconds. So let's do that. We can configure a frequency of 10 for our second probe, and then go back to the first probe and enter IP-SLA configuration mode and set up a frequency there. Notice that once you set up the type of IP-SLA, you will go straight into the configuration mode for that type. Our initial configuration mode was IP-SLA. You defined the type. It's type echo. It will be different depending on the type of probe you select. So now our IP-SLA number 99 has a frequency of 10 seconds. One key step is to schedule the probe to initiate testing. We do this with the IP-SLA schedule command. In our example, we will initiate the IP-SLA now with the keyword now and set it to run forever. Just for the sake of our example, you can also define start times and other types of duration with this command. Verifying the IP-SLA probes is critical at this point, before we tie our routing process to the probes. Again, if the IP-SLA operation is misconfigured, it will be much more difficult to troubleshoot later. So, we use the show IP-SLA monitor configuration command to display the configuration for each probe. In this example, number 99, such as frequency, target addresses, scheduling, and other parameters. This is telling us that the probe has already started. So, let's use the show IP-SLA statistics command to display the number of successes, failures, and the results of the latest operations. In our example, probe number 99 has already started. We can see the start time and the latest return code. We can also see that the operation has succeeded 16 times already. Same for IP-SLA number 100, 15 successful probes and 0 failures. So, our probes are being successful. Let's go on to our next step, which is to create the tracking objects. We need these tracking objects because they are the ones attached to static routes in order to redirect routing. So we need to use the track command. The syntax is represented here in the top right panel. It's only a partial syntax with the options that we are using for this scenario. Notice that the RTR keyword allows us to tie the object tracking feature to the IP-SLA probe. For instance, this number 99 is really in reference to the IP-SLA definition identified with the number 99. The number 1 here is a reference to the object tracking definition. So, 1 is the parent of 99, and, therefore, 1 is the object that we are going to attach to static routes later. The track command goes straight into track configuration mode, as you can see. Here you can define multiple parameters. One of the most important parameters is the delay command. With it, you can define a level of sensitivity change in tracked objects. Briefly, with delay, you can alleviate the effect of flapping objects by specifying the amount of time to wait before notifying about the success or failure of the probe. In our example here, we are going to configure 10 seconds of down relay and 1 second of up relay. This means that it takes 10 seconds to notify the bad news and only 1 second to notify the good news. If the DNS servers fail just momentarily and come back up within 10 seconds, there is no impact in routing and no changes because the good news is spread faster. Because we have 2 ISPs, we are going to need to add a second tracking object, attach it to our probe number 100, and specify a similar delay. So, our IP-SLA probes are working and reaching the DNS servers. They have been assigned to tracking object definitions. It is finally time to align our routing function on R3 to dynamic DNS tracking. You can do this in simple terms by using the IP route command to create static routes that appear or disappear, depending on the success or failure of the IP-SLA operation. Here is how it's done. The tracking options at the end of the static route command For our first tracking object, refer to the tracking object number 1. We use this to associate the tracking option to the default static route, pointing to R1 as the next hop. Notice that this is not the IPSLA number that the tracking object created with the track command. Remember, the tracking object then makes a reference to the IPSLA number, which, in this example, is 99. We need to do the same for the second static route pointing to R2 as the next hop, and then we need to verify. As we display our routing table, we can see that both static default routes are inserted in the table. Now let's test how this behaves under failure conditions. Here's the command we are going to use. Before I initiate any testing, I'm going to debug IP routing, a very helpful command that illustrates the operations of the routing table. However, it's equally dangerous and not recommended to use in a production environment. Let's try to shut down one of the DNS servers. They are simulated by loopbacks on R1 and R2. Let's go into R2 and shut down the loopback. If we go back to R3, we can see how immediately the route to that loopback via our connection to R2 is deleted by EIGRP. Look at that. It is briefly followed by the removal of the static default route toward R2. Let's just undebug this so we aren't bothered by the output of the debug. But again, we can clearly see how the route removal was toward that DNS server, the object that we were tracking. Then about 10 seconds later, the static route is removed. We can quickly check the Show IPSLA statistics. This was R2, so it means it's IPSLA number 100. And we can see the number of failures because the tracked object is down. The Show IP route command clearly shows that only one default route remains via R1. Now, let's turn Debug IP Routing on again and see what happens with the good news. If I enable the loopback again, I can see that the route was reset, pointing to the 10.0.8.2 DNS server. Almost immediately, we can see the static routes being added again. Now both entries are there in the routing table, and we are still load balancing toward both ISPs. Now let's debrief. Think of the possibilities with object tracking and IPSLAs. We can probe based on reachability and, in that way, change routing operations and do path control, which is the ultimate objective of this lesson. This is a very powerful statement. We can also do the same performance metrics through Cisco IPSLAs. We can change paths based on network conditions, such as delay, load, and other conditions, not only based on the liveliness of a certain object or host. This is partially what Cisco IOS Optimized Edge Routing, or OER, does. It's very powerful indeed. In deploying this type of configuration, we should consider the impact in terms of additional probe traffic that we are generating and how that will affect bandwidth utilization and congestion levels. Tuning your configuration becomes critical if you want to mitigate possible issues related to excessive transmissions and route changes in the presence of flapping tracked objects. Also, notice that there are alternative solutions and configurations that accomplish the same result, but will be more granular and specific to support other options. For example, policy-based routing, in this example, points to next hops that are tracked via IPSLAs. Because of the use of route maps, this configuration gives you more granular options to define via access or prefix lists, and which traffic classes will be subject to changes based on the results of the tracking. For instance, you can reroute voice, mission-critical data, and others using this solution. In summary, this lesson was a good way to see the technologies in action and practice our path control strategies with real-life scenarios. This included redistribution scenarios and IPSLA routing through object tracking.